All right, so if there is one thing we learned in the previous presentation, it is that logs are useful for attack investigation. In fact, logs are so useful that 75% of incident response analysts consider them the most valuable artifact during the course of an investigation. Now, in fact, there are also a lot of tools that, from the industry that allow analysts to analyze the logs. However, because logs are so valuable, it is a common attack pattern for adversaries to tamper with them and inject new log entries or manipulate existing log entries or forge or delete log entries in an effort to cover their tracks. And this phenomenon is quite widespread. In fact, 72% of the analysts have reported encountering it during the course of an investigation. And we have seen attacks in the wild that also engage in this type of behavior. Now, because logs are so important, let me just describe to you what the logs that we care about are. So we consider an attacker who can compromise a machine using the following steps. So first of all, the attacker will achieve initial access by exploiting some publicly facing service. And then they will use this initial access to establish foothold. So for example, by running an unprivileged shell. They will use this shell to download an exploit. And then finally, they will use this exploit to achieve privilege escalation. Now, because in commodity operating systems, root access is all that the attacker needs to tamper with the log files, after step 4, they are free to engage in log tampering and manipulate the log. Now, the logs that we care about are the ones related to the compromise, from steps 1 to 4. And the reason why we care about them is that because if the attacker does not tamper with them, then we can detect the attack with existing tools, like we saw in the previous presentation. However, the problem is that if the attacker does tamper with them, with existing tools, we can't really detect the attack. So that's really a limitation of existing solutions. So in this research, we want to build a system that can detect the attackers even if they engage in log tampering. So our goal is really to detect the log tampering so that even in the step 2, we are really forcing the attacker into a lose-lose situation. This type of attacker will not be able to go undetected, because if they do not tamper with the logs, they will be detected by forensic tools. But if they do tamper with the logs, they will be detected by our system. Now, before I go any further and I tell you how we do it, let me make 2 clarifications. So first of all, I said the logs that we care about are the ones from steps 1 to 4. Now, in our threat model, we assume an attacker who can compromise machines, and not just the one that they compromise, but can engage in lateral movement. So storing the logs somewhere else, like in a central server, is not enough. So what we want to do instead is that we want to generate proofs of integrity for the logs, so that when we record them on the host that actually generate these logs, we have proofs, and then wherever we store the logs, we can later check these proofs to detect if they have been modified. The second clarification that I would like to make is that there exist prior solutions in cryptography and also in systems that provide this property. However, what we saw, and this is in fact our key motivation, is that none of the prior solutions really can scale to high volumes of system logs. So modern operating systems can easily generate thousands of system calls per second. And if we want to monitor all these events, we need a solution that is practical and that has scale efficiently to log all these events. And as I will demonstrate later, our system is the first system that can really scale to such volumes. Now, before I tell you how we actually achieved that speed up, let me give you a high-level overview of the components of our system, which we call Custos. So first of all, we present a Tamper-Evident logging protocol. And this protocol enables a logging machine, so a host, to record logs in such a way that any tampering with them can later be discovered. The second component is an auditing protocol. And the goal of this protocol is really to detect and to discover as quickly as possible, and as we will see later, in real time almost, if any logs have been tampered with in other machines in the network. So the first one is a component that works on a single machine, while the second one, auditing, works among multiple machines. Let's start from the first one. So the key idea, what really makes our approach practical compared to prior solutions, is that we decouple the cost of generating the proofs with cryptographic schemes from the cost of actually creating and recording the log events. And so we take really the signature generation part, the proof generation, outside of the critical path so that we can actually achieve a larger speed up. And the way we do it is that we do it by leveraging features of trusted execution environments. So we assume that a machine has an enclave, and that we have an identity of each machine, which has a secret key that is generated and stored inside the enclave. And then we generate signatures using the following scheme, which is a standard signature scheme. And in this scheme, we just hash a lot of log events together with a counter to ensure the chronological ordering. And then we generate a signature over the log events. Now, as I said, what allows us really to achieve the speed up is decoupling the two operations. So what we do is that we store a current hash together with the counter inside the enclave. And when log events are generated by the operating system, all we have to do is really to just update the hash. And the reason why we can just do this is because the hash is stored inside the enclave. And so that means that it is out of reach even after achieving root access for the adversary. Now, let me give you an example. Let's assume we have, at some point in time, this host generating H log events. So when the first log event is generated, we can update the hash with the first log event. And then at a later time, the second log event is generated, and we update the hash again. And all the way down to the last event, we just update the hash. And that's all we need to do. Now, you might be wondering, when do we actually sign this hash? Because I said the scheme has a second component, which is signing over this hash. So what we decide in our design is to sign these logs only when it becomes necessary. So we introduce the auditing component, and let's call this auditor. In some prior work, it's called verifier. And this auditor will request at some point from the logger a proof together with the logs. And so it is at this point that the logger will commit the hash that is stored inside the enclave by updating the hash with the counter and generating a signature over it, and then reinitializing a hash so that new logs can be logged later on. Now, I introduced this auditor component, but I haven't really described it to you. So let me just tell you who is this auditor and how does it work. So in our paper, we describe two types of auditor. One of them is a centralized auditor. And the centralized auditor is really meant to be integrated with existing common practices in companies. So existing common practices are to just stream the logs to a central server. And what we do here is that we just make the central server request proofs from the logging machines inside the network together with the logs. And we show that this incurs very low overhead, and it can really be applied and deployed without a lot of changes to existing solutions, because we do not require changes to the way that logs are actually parsed. The second type of auditor that we introduce is a decentralized auditor. And this one is meant for threat models where we don't want to rely on only one central point for the auditing component. So it looks more or less like this. We have many machines inside the network, and each of them is both logging and auditing other nodes in a peer-to-peer fashion. Now, in the paper, we describe how this decentralized auditing can be configured. But for the sake of this presentation, I will just give you an oversimplified view of how an audit looks like when we have one auditor challenging one logger. And here's how it looks like. Let's assume we have an auditor Z that at some point in time decides to request proofs and logs from logger V, whose public key is known. Z will generate an audit challenge by sending a request to the logger V. And logger V, as we saw earlier, will generate a proof using the scheme that we saw earlier, and then send this proof together with the logs to the auditor Z. At this step, auditor Z, all it has to do is that it has to verify that the proof and the logs are matching. So they will recompute the hash with the same way that the logger has actually done it, and then run the public key verification scheme to verify that the proof is correct. Now, does this actually work in practice? Well, let me give you an example of a node that is compromised and then challenged by an auditor. So we have logger V, and this logger is, at some point in time, target of an attack. And so during this attack, we have, as I said, some steps that the attacker has to do, where they will, first of all, gain initial access and all the way down to privilege escalation. During these 4 steps, some logs are recorded on the machine. And these logs are going to be hashed inside the enclave. But now, after the adversary achieves privilege escalation, the logs will be modified because the attacker will tamper with them. Now, recall that these logs, even though they have been tampered, they were originally hashed inside the enclave. So the attacker cannot really update the hash inside the enclave. So what happens at a later time is that if an auditor requests a proof to the logger will commit the current hash and then send the logs which have been tampered together with the proof to the auditor. Now, because the hash was computed over logs that were different from the logs that were sent to the auditor, since they were tampered, the verification will fail and an alert will be raised. Now, in the paper, we provide a full security analysis, even in the case of a compromised auditor, and I encourage you to check it out. But I also want to demonstrate and go back to the previous point that I made, that our system is really the first system that can scale to large volumes of system logs. So we really want to make our system practical. And now I will demonstrate to you what I mean by that. So we compared our system with the state-of-the-art secure logging solutions, both in the cryptographic space and in the system space. So as I said, our system is called Custos and will be the first one in the line. And then we have compared it with SGXlog, which is a prior secure hardware-based scheme. And we have also compared it with BGLS, which is a cryptographic scheme. And this is the cost of logging one event. So when we have to secure one single event, this is the cost that we incur in the existing systems. So in Custos, it takes just about 1 microsecond to log an event, because all we have to do is really just update a hash. In prior work, even the state-of-the-art and the fastest solution takes about 1 millisecond at best. So that means that with Custos, we can scale all the way up to 1 million events per second very easily. And that's good, because commodity operating systems can generate thousands of system calls. So if we have a high ingest rate, that's good. The problem is that prior work at most can really scale to about 1,000 events. And that's good in certain circumstances, like application logging. But as we said, in system logging, where the events that we're logging are the system calls, we need something faster. And so this demonstrates that our approach actually can scale. The second result that I want to show you is how our system affects existing applications. So say we are running applications on the machine, and since we are really decoupling the costs of logging and generating signature, do we actually incur any costs for real applications? Well, luckily, the answer is no. The cost is really just like 1% to 7%, even in the highest CPU-bound benchmark that we ran. So this is good because it demonstrates that our system is practical. And finally, I want to show you a case study where we demonstrated an attack. And we show how our auditing protocol was able to detect log tampering in a timely fashion. So we took our auditing protocol and we deployed it on 100 nodes inside a data center. What we did is that we then considered the case when one of these nodes was compromised. And the pattern of the attack followed the one of the DARPA transparent computing engagement dataset that was described in the previous talk, that was carried out by a red team. And we used this attack and we enhanced it with log tampering. So since we saw that if the attacker does not tamper with the logs, they can be detected. We wanted to see, can we actually detect it even if they tamper with the logs? So the attack looked like this. At 10:52, the attacker was trying to compromise the machine, but failed. Then later on, at 11:42, the attacker gained initial access and an unprivileged shell. And then 4 minutes later, the attacker was finally able to complete the attack. But let's see the last minute of the attack and how the attack was completed and how we actually play a role and help the defenders in this case. So the last step of the attack was really to download Dracon, which is an exploit for privilege escalation, and then use Dracon to achieve root access. And immediately after root access, what we did in this attack is that we ran this Dracon binary to achieve log tampering. Now, as I said earlier, in our auditing scheme, the goal that we have is to discover this type of behavior as quickly as possible. So what happened in our setup was actually really good. 3 seconds later, Custis detected and discovered log tampering and reported it to us. So that was really a good result because it shows that this type of attacker was forced into a no-win situation because they tampered with the logs and we detected them. And that was also scaling to a real-world attack scenario. Now, in this talk, I motivated that log integrity is important. In fact, it is a widespread phenomenon for attackers to engage in log tampering. And this is concerning because, of course, logs are useless if they were manipulated. But I also show that we can have a solution for that. And in fact, Custis is a practical solution for the log integrity problem. And we can record logs in such a way that any tampering with them can be detected. I also showed to you that our system can be extended with the auditing tool, which can discover this tampering in near real time. In our case, it took only 3 seconds to discover log tampering. And finally, we have implemented our system and made it available as open source online. So I encourage you to try it if you are interested in this type of research. And with this, I thank you for your attention, and I am happy to take any questions.
Yeah, great work. I think this is a really important problem, and then I really enjoyed your talk. And I have a question that actually this problem is become more serious for like some isolated devices like IoT and things like that. So it seems like that your solution depends on some kind of hardware primitive here. So can we minimize the platform dependencies or abstract away? And that is my first question. And my second question is that you are actually building like a trust chain using the P2P like a manner. So where there is not easy to find those shares. Let's say your device is one device is in this place, another one is too distant. So how do you think about those problems?
All right, so let me rephrase your two questions. So the first question was, can we do this on machines that do not have heterogeneous environment? So the answer is we only implemented this on Intel SGX as a trusted execution environment, but our design is agnostic to the trusted execution environment. So it really can support other devices that maybe do not have SGX, but have some other type of trusted execution environment. So the answer is yes, it can be extended to work with that. And we describe in the paper the primitives that we need in order to support our design. So the second question you asked was, what if the auditor... Yes. Yeah, so that in our case, we deployed this on a data center where all nodes were aware of each other. And, but this could be extended as long as the nodes know of each other to scenarios where the two nodes are far away from each other, as long as they are aware that each other exists. So yeah, it would support that too.
Great, thank you.
Yeah, you're welcome.
Hey, thanks for the talk, Arjan Ostik from UC Irvine. So since this is an Intel SGX enclave, the execution is actually controlled by the host. So if there's a malware on the host and it just shuts down the enclave, how do you prevent that state being lost, the hash that is kept inside the enclave?
Yeah, so what we do is that in our threat model, let me just rephrase your question first. So you asked me, what happens if the adversary takes control of the machine and then shuts down the logging?
Yeah.
Well, that's fine, because what we care about, as I said earlier, is really the logs that are recorded before the attacker achieves root access. And those logs that have been hashed inside the enclave before compromise are the ones that really we want to care about. The ones after are really, we cannot really prevent the adversary from stopping logging after that. But if we audit the node and the node does not reply, that already by itself is a suspicious event that can alert us that maybe there is something wrong with the machine.
But if there was no audit before, then you would no way of knowing what happened before two audits if the enclave is actually shut down.
So what we have is that we have two types of shutdown. There is like a regular shutdown when you shut down the enclave, and this is supported in our design by basically sealing the current state to disk and then taking it inside the enclave after startup. And we describe this in the paper. The second type of shutdown is a forced shutdown, so when we crash the machine. But in that case, the next time we actually audit or we turn on the machine, the logger will not be able to prove the integrity of the logs. And so in this case, by itself, this fact will be a subject of will just make us suspicious and will generate an alert. So in this case, if the attacker tries to stop logging, we can still detect them because they are not able to provide us any proof anymore. They're just not following the protocol anymore.
OK, thank you.
Yeah.
Hi, Xander Work from Oregon State. So I definitely see how this can prevent an attacker attempting to remove log entries or modify them, but how can this prevent an attacker injecting a malicious log entry using the API used by the logger that you've
Yes. So the question is, how can we prevent the attacker from injecting new log entries using the API of the logging framework? So the answer is that the attacker is free to actually do that after they achieve root access. But again, that's fine, because in our threat model, all that we care about are the logs recorded before compromise, because those really contain the root cause of the attack. So how did the attacker access the machine? How did the attacker achieve privilege escalation? Those are the questions that we care about. And everything that happens after privilege escalation is really something that maybe we can leave to future discussions. We don't solve that problem.
Great, thank you, appreciate it.